Hello and welcome to the second part of this video about the wave behaviour of light. In this video we'll be looking particularly at radio waves. So radio waves are electromagnetic waves with long wavelengths and low frequencies, and they transmit TV or radio signals. From our wave equation, we can see that if we were to rearrange speed equals frequency by wavelength, we could end up with frequency is equal to speed divided by wavelength. So the frequency of a wave is inversely proportional to its wavelength. So that means that if the wavelength of a wave is small, the frequency would be large. If the frequency or if the wavelength of the wave was large, then the frequency would be small. A German physicist called Heinrich Hertz devised an experiment back in the 19th century which was designed to produce and detect an electromagnetic wave in the lab. He did this by applying a high voltage of alternating current across two wires, which are separated by a small gap, as we've kind of got in our graphic here. With the current oscillating across the gap, a changing electric field and therefore a changing magnetic field would then propagate as electromagnetic waves. The direction of the electric and magnetic fields change as the current changes direction, so as the current alternates. This continuous oscillation of current produces the changing electric and magnetic fields that propagate away from the antenna with the speed of light and with a frequency equal to the oscillation of the current with whatever frequency it is alternating at. So in our first diagram, the positive terminal is here, the negative is here, the current is moving upwards, and the electric fields are running from the positive side of, or the positive wire to the negative wire. So remember, electric fields run from positive to negative. Therefore, a magnetic field is induced, and it's induced in a direction that is pointing into the page. The current in the second image has switched directions, so it's an alternating current, it's switched directions. Now the positive wire is the bottom wire and the negative wire is the top wire. The electric field is still going from positive to negative, so it means the electric field has switched directions, and because the electric field has switched directions, the magnetic field is now pointing out of the page. So it's this shifting of electric field and therefore magnetic field resulting from the change in the direction of the current. It's this that allows the electric field and the magnetic field to reproduce each other, and for this electromagnetic wave to first of all be produced and then to propagate itself. The transmitted electromagnetic wave, which in this case is a radio wave, induces an alternating current that oscillates with the same frequency in the elements of a receiving antenna. So once this wave that is propagated from the transmitter antenna is received by the receptive antenna or the receiver, then a current, which is the same as the original current, is induced, or rather the alternating current that is induced is the same frequency as the original alternating current. When the electric field lines are closer to the source, they form closed loops, so closer to the conductor. The loops that they form are closed, but as they get further away from the conductors, the field lines flatten out, and they're referred to as plane waves. So we've got some plane waves here, and these are loops here. When they get closer to the receiving conductor, the plane waves will form back into loops. So the reception of radio waves depends on the shape of the conductor. If you've got a linear conductor, so I should have put a picture in, but the conductor that has like just a bunch of prongs hanging off it, so a linear conducting element, the change in electric field of the radio wave exerts a force on all of the electrons in the conductor. So these electrons will oscillate with the frequency of the wave. If you've got a looped conductor, the change in magnetic field of the radio wave induces an EMF, so a potential difference or a voltage in the loop, and current is therefore induced to flow. And this current in the loop will oscillate back and forth with the frequency of the wave. So for both linear conducting elements and loops, the oscillating current in the receiver is decoded, and then the image or sound, so whatever is being transmitted via this wave, is reproduced. So reproduced on the telly, reproduced on the radio. I'll just quickly flag that I've added on some extra success criteria to this video. So you'll also need to be able to relate the orientation of the receiving antenna to the plane of polarization of radio or television waves, and you'll need to be able to solve problems using the wave speed formula. So speed equals frequency multiplied by wavelength. To relate the orientation of the receiving antenna to the plane of polarization, you'll need to know what the definition of plane of polarization is. So this is the plane of the electromagnetic wave that contains the electric field vector. So in our image here, the electric field is vertical, so the plane of polarization would be the vertical plane, so the Y plane in this picture. If a wave is plane polarized, it means that the electric field oscillation is restricted to a single plane. So you can have situations where the electric field shifts through different planes, or there might be multiple different electric fields that are oriented in different planes. If something is plane polarized, then the electric field oscillation is just restricted to one plane. The plane of polarization determines the orientation of the receiving antennae. So elements of antennae, so they're like metal prongs that are sticking off, are oriented in the same plane as polarization of the received electromagnetic waves. So if the plane of polarization is vertical, then the elements of the antennae will be vertical. If the plane of polarization is horizontal, then the elements will be horizontal. This orientation, whatever it is, ensures maximum reception, and it also ensures that the electrons in the element oscillate with the same frequency as the frequency of the electromagnetic wave. In metropolitan Adelaide, the TV antennae are horizontal because broadcasters in metro areas emit or transmit waves that are horizontally polarised. In rural South Australia, so where we are, the antennae are usually vertical because rural broadcasters tend to transmit waves that are vertically polarised, and this is to minimise interference with metropolitan transmitters. So we're going to have a look at wave formula for electromagnetic waves. all electromagnetic waves have a velocity or a speed that is equal to the speed of light, which is represented by c. And you'll just need to remember, actually it'll be on your formula sheet, but it's easy enough to stick in your head anyway, that the speed of light is equal to 3 by 10 to the 8 meters per second. This rule is exactly the same as velocity or speed equals frequency multiplied by wavelength, but instead of having v, we've just got c listed because c represents the speed of light, and it's the same for all types of electromagnetic radiation. So the speed of visible light is the same as the speed of ultraviolet light, it's the same as the speed of infrared light, it's the same speed as a microwave, as an X-ray, gamma ray, etc., radio wave as well. So if you have a question or a problem that you need to solve about an electromagnetic wave and you've been given a frequency and you need to find the wavelength and you haven't explicitly been told what the speed is, you can assume that it's 3.0 by 10 to the 8 because that's the speed of light, and that is what the speed of electromagnetic radiation is, any form of electromagnetic radiation. So I've got an example. Mobile phones use radio waves to send and receive information. What is the wavelength of a radio wave if its frequency is 900 megahertz? So we'll write down what we do know. Its frequency is 900 by 10 to the 6 megahertz. And we know that the speed of the wave is the speed of light, which is 3.0 by 10 to the 8 meters per second. And we're looking for lambda. We know that the wave speed equation or formula is speed equals frequency by lambda. We're looking for lambda, so we'll rearrange this to be lambda is equal to speed divided by frequency. Speed is equal to 3.0 by 10 to the 8 meters per second. Frequency is equal to 900 megahertz, so 900 by 10 to the 6. Pop that into a calculator and you'll end up with a wavelength of 0.33 meters. So that is the wavelength of a radio wave if its frequency is 900 megahertz, 0.33 of a meter, so a third of a meter. Next question, calculate the frequency of violet light with a wavelength of 400 nanometers. So we know that the wavelength, lambda, is 400 nanometers, so 400 by 10 to the negative 9. We know that velocity, or speed of the wave, is equal to speed of light, which is 3.0 by 10 to the 8 meters per second. And we're looking for the frequency. So we'll write our wave rule, speed equals frequency multiplied by lambda, and we'll rearrange this to make frequency the subject, so frequency is equal to velocity divided by lambda. So that is 3.0 by 10 to the 8 divided by 400 by 10 to the minus 9. I can't remember if I said minus before, but nano is definitely to the minus 9. Pop that into your calculator, you'll end up with a frequency of 7.5 by 10 to the 14 hertz. So the frequency of violet light with a wavelength of 400 nanometers is 7.5 by 10 to the 14 hertz.